We will start with Elsie Starkenburg, who is going to tell us all about the local group Dwarf Galaxies and streams. Elsie, I will just let you know for 2 minutes, if it's okay. Thank you.
Thank you very much. I will start sharing my presentation. Good afternoon, good morning, everyone, and thank you very much for the opportunity to talk about all that UVES has done for local group Dwarf Galaxies and streams. So just a little disclaimer here before I start the talk. I realized very quickly that it will be impossible to talk about everything that UVES has done in this field, as is shown by just a simple search on UVES and Dwarf Galaxy or UVES and stream. So this talk is a very personal and rather incomplete summary of this field. So just to get everybody on the same page, I just want to give a little bit of introduction into the framework. So dwarf galaxies are very interesting in their own right because they show a range of masses and star formation histories, which means that you can study in much detail for the dwarf galaxies that are nearby. You can study in really much detail how galaxy formation proceeds in different types of environments. So for different star formation histories and for a wide range of masses. We also think they are pretty important because in our lambda CDM framework, think about it quite naively, then the idea is that bigger galaxies are formed out of smaller galaxies, and that in particular old stellar components like the halo of the galaxy is formed out of destroyed smaller galaxies, smaller dwarf galaxies. And we know this picture must be to some extent correct because we see this process happening, for instance, to the Sagittarius dwarf galaxy, which has been completely disrupted, and there's stellar streams that basically wrap around the galaxy coming out of this object. But it was the question when UVES came online, how much the surviving systems that we still see as coherent dwarf galaxies today in or around the Milky Way halo, how much they are like the building blocks that formed most of the stellar components of the mixed Milky Way halo. So when UVES joined the game, there were very few detailed observations of stars in dwarf galaxies available. And as we already first two giants studied in the Sagittarius dwarf galaxy by Bonifacio et al. 2000. But this field really kicked off, I think, then when Citron et al. In 2003 studied 15 red giant stars in the galaxies Sculptor, Fornax, Carina, and Leon 1. So the same team had already looked at some northern dwarfs, but as most of the dwarf galaxies that were known at the time are in the southern hemisphere, UVES was really a key instrument to get this going. And the results that they got from this study were very, very surprising. So what they found, and what numerous other works have shown since, is that the dwarf galaxies do not have the same abundance patterns as known halo stars. And to show this, I will show a compilation of stars. So in the color points, you see stars from the dwarf galaxies Sculptor, Carina, Fornax, and Sagittarius. This is a compilation from Tolstoy, Hill, and Tosi in 2009. And in black, you see the Milky Way stars. So what you see is that even though they span the same metallicity range, which is on the x-axis, what you see is that they have a very different, abundance pattern in calcium over iron, which is on the y-axis. And so the simple picture of just smashing together a Sculptor, Carina, Fornax, and Sagittarius and make the Milky Way halo, that doesn't work. So how do we interpret this? So what is the basic picture is that there is a different contribution from supernova type 2 and supernova type 1a products at a similar metallicity. And the reason for this is that these products have different time scales. So supernova type 2 are from massive stars and supernova 1a are from low mass stars. So if a galaxy is evolving very quickly and enriching very fast, then it's at the beginning, it's mainly dominated by supernova 2 products. But then at a very high metallicity, there's this 1A products coming in, which is basically the red line you see on the right. But if you have a very small galaxy that is evolving very slowly, it will not get to such a high metallicity before the 1A products start to kick in and produce a lot of iron, which reduces the alpha to iron ratio. So this is the main mechanism that we think that causes this difference. There is possibly also an influence of the initial mass function in the system. So in the bottom panel, I'm showing the same thing, but now more observationally, where you see 3 different systems highlighted or 3 different populations highlighted. So stars that show kind of the red abundance pattern, we think come from small systems with a very slow evolution. The green stars are from intermediate mass systems, and then the blue stars are from massive systems that only have this turnover at very high metallicity. Now there is this part of the diagram where they overlap in the beginning. So this raises the question if the earlier phases of star formation are more universal than the later phases, and I will come back to that. At this point in time, SDSS comes along, and SDSS brings the discovery of many more dwarf galaxy systems. So on the left, you see the picture as it was when UVES came online, and then on the right, you see the picture after SDSS. So there's especially a lot of fainter systems that SDSS discovered over time, especially in the Northern Hemisphere. And even though they were in the Northern Hemisphere, UVES has played also a very important role in studying these new systems. So what we see is that there's no clear kick-over of this alpha element population. So they're probably all old stellar populations. But we do see a difference in the heavy elements, which we believe is connected to implications for the sites that make these elements. So in this community, people have been talking about neutron star mergers, for instance, way before they were really shown in gravitational wave experiments. And this is shown here. So you see a heavy element strontium, and you see that in Sculptor, which is the orange points, and in the Milky Way, which are the gray points, you see that the pattern is very different from the ultra-faint galaxies, which are in black. I just want to highlight here a very recent paper that shows also the importance of these heavy elements. So Recio Blanco et al. 2020 is showing the difference between yttrium and europium. So yttrium is mostly produced in the slow neutral capture process, and europium is mostly produced in the rapid process. And what they show is that there might be a dependence on the mass of the system in which these stars are formed, even at the metal poor end. And this is shown in the bottom panel here. So even when you cannot distinguish anymore where a star is formed based on its alpha elements, as I was showing before, you might be able to say something from the yttrium to europium abundance pattern. And why is this interesting for this discussion is that these types of elements, they need really high resolution to be observed, and they need high efficiency in the blue, which means that something like UVES is ideal for this. I also want to highlight that UVES has been observing many special stars inside of these systems. So the ultra-faint galaxies, but also the normal dwarf galaxies, they contain a lot of these interesting, extremely metal-poor stars. And these stars provide us important clues for early chemical evolution just after the Big Bang. Particularly well studied among the ultra-faints are Bootes 1 and Segway 1. And for instance, in Segway 1, there was a first discovery of a carbon-enhanced, extremely metal-poor star. And in these stars, we think that the carbon that they have, that is really from a first star. So this really is the product of a first star exploding and then leaving these products for a second or third generation star to form from. These stars were also discovered in some of the more classical dwarf galaxies, and there was a first discovery of a carbon-enhanced metal-poor star in the Sculptor dwarf galaxy by Ausa Skouladottir in 2015. And just to illustrate the kind of beautiful abundance patterns that you get, so here in the bottom, you see all of the different elements that could be measured for these stars. And so what you can do is you can fit the predictions for different types of supernovae to these patterns and understand what happened before the star was formed. And so in this case, it fits very well the pattern of a faint supernova that we think only exists in the very early universe with a normal, more normal supernova products. These discoveries just keep on going. So I just want to highlight a very recent one by our friendly chair, Spardone et al. 2020. That is a first carbon-enhanced metal dwarf star with an RS pattern in Sagittarius dwarf spheroidal, and basically the clearest example that we've seen of such star in any dwarf spheroidal. And here, just to illustrate maybe to people not in the field what kind of exotic phenomena we can study, is the best explanation here is a mass exchange from an AGB companion system enriched at a very high concentration by the yields of a neutron star merger. So this is quite exciting physics that actually UVES can probe in these systems. Now, of course, I want to talk not just about the dwarf galaxies, but also about the streams that we can observe with UVES. There, the problem is that the target densities are generally lower, but it can be that these streams are more accessible because they're all over the sky. And also, if you want to get a complete picture of the dwarf galaxy that entered the Milky Way system, you better look at both the body and the stream, because there might be metallicity gradients in the system, meaning that the streams are much more low metallicity than the body was. Detailed UVES follow-up really there gives us insight in the nuclear synthesis processes that happened in the parent galaxy before it was entering the Milky Way. So here, just an example. This is Hansen et al. 2018, where again you see a lot of detail that can be measured. And in this case, she was studying Sagittarius stream stars at low metallicity, complementing studies that happened already in the body. And what came out of this study is that you need, in order to explain the abundance patterns here, you need a mixture of low and high mass stars. And this again then feeds back to the discussion on the IMF. So in this case, they found that no top light IMF could reproduce this. Now, streams are not always the kind of coherent things that we have in mind. And I think one of the most interesting works, including UVES data, was Nisa and Schuster in 2010. So where they studied halo stars in much detail. So what they found is that these halo stars fall into two populations, clearly again separated in alpha over Fe. So alpha elements over iron elements, like so alpha elements like magnesium or calcium that we saw in the beginning. The kinematics of these low alpha stars suggest that they have been accreted from dwarf galaxies, is what they already suggest. Now that we have Gaia satellite data, we know this is very much the case, and that actually what they have been seeing is this debris from a dwarf galaxy that's now been called Gaia Enceladus, or even the Gaia sausage, which was a galaxy slightly more massive than the SMC is now, which is really dominating the inner halo by its debris. And here you see the current day picture from Gaia and also from other spectroscopic surveys. And it really shows that there is this low alpha tail that these stars populate. Finally, I just want to highlight that UVES is not just very suitable for studying stars, it's also very well suited for line absorption studies towards background sources such as quasars. An example for this is the Magellanic Stream. And now I'm really out of my comfort zone, but I picked this study, I saw this study where they study a ribbon of gas trailing the LMC and the SMC orbit. So this is UVES data combined with ultraviolet data from the Hubble Space Telescope. And what they see is a very surprising complex structure with many different abundance patterns along different sidelines. So what they argue is that there might be a mixture of mostly SMC material and mostly NMC material in different parts of this stream. So showing a very complicated picture there. So in summary of the past work, I just want to highlight that I think UVES has been absolutely instrumental for our understanding of dwarf galaxies and streams. It's been doing some of the first detailed chemical analysis of stars in these systems. And it's also been looking at very special stars that tell their own stories. It's been looking at stellar abundances, it's been looking at gas abundances, from the biggest dwarf galaxies to the smallest satellites, and from very coherent streams to very phase mixed material that really tells us stories about the main building blocks of the galaxy. So I guess we're all here to discuss how can it keep such an important role also in the future. Now to start, I really want to highlight something which I think is key for this, this science case, is that UVES has been instrumental on its own, but it's even more valuable, I think, because of the combination with other instruments that we have on Paranal. And in particular, flames, which has been very useful in this type of study, because of course, dwarf galaxies in particular, you have many, many stars relatively close together on the sky. And the 8 fibers that feed UVES in every flames field have been very valuable cross-check for multi-object work and to access more elements. So UVES fibers both have a higher spectral resolution and a larger wavelength coverage than the flames fibers themselves. Also within the teams that I've been working with, we've been using X-Shooter in combination with UVES, where we use UVES for the brighter stars and X-Shooter for the fainter stars in the same system. So as the future of this field is concerned, so for dwarf galaxies, we're discovering more and more of these, but mostly now very faint and very sparse systems. So that means they're actually quite well suited for UVES. This is also in particular true for streams. So there's more and more discoveries of very faint streams. These are not just interesting from a chemical point of view, but also very important measuring tools for the galactic potential and acceleration field. And also this is a wonderful science case for UVES. And I'm showing here an example of the work of Rodrigo Ubata, who has been finding a lot of these faint streams and following them up, where UVES provides crucial radial velocity information to constrain the galactic potential. So for the coming years, there's a lot of multi-object spectrographs that are coming online, and I think we should see UVES in this kind of landscape. So these are the two that I'm most familiar with, UVES and Foremost. So they're both on 4-meter telescopes with a resolution of about 20,000. And there's about 1,000 fibers that can be used in a high-res mode. Now for UVES, you have to choose whether you want high-res or low-res. And for Foremost, these will be observed simultaneously. So every field Foremost observes, there's about 800 fibers that will be observed in high resolution. For UVES, there are 2 arms where you have a choice for the bluest arm, which wavelength region you want. And for Foremost, there are 3 arms covering the wavelength regions that I'm showing here. That also means that these distinct wavelength regions means that they do miss some key elements. So for instance, in Foremost, a lot of it is covered, but they, for instance, miss zinc, which is an important element if you want to compare what happens in the local universe, for instance, with DLAs that you see at higher redshift. And it also means that UVES can add really here. I mean, there's a factor of 2 in resolution. There's a factor of 2 in telescope diameter. And of course, there's the extra wavelength windows, particularly useful in the blue. So I think, especially for these heavy elements that I've shown to be key, that are mostly measured in the blue, this is very important capability. In the future, I think this community is moving towards a situation where we have such a facility on the 10-meter class telescope. And there's already plans for a Mauna Kea spectroscopic explorer that might replace the Canada-French Hawaii telescope. And also in the ESO community, there's been a lot of talk about this. This is clearly something that the community is thinking about. So how do I see UVES in all this? I think UVES will still have, for the years to come, a very important role as a follow-up machine for the exciting new discovery space that is opened up by massively multiplexing spectrographs. I think it should focus on what other instruments cannot deliver. So especially the sensitivity to key elements for more metal poor or fainter stars. And these are in particular also many heavy elements that are found in the spectrum. There might also be a consideration here on how you allow users to get a very fast turnaround on exciting objects that come out of these multi-object spectrographs. So what we already have in place are directors' discretionary time and targets of opportunity proposals, but it might be a good opportunity to think if that is sufficient for users to really, for ESO users to really make the most, for instance, of foremost ESO discoveries that you then want to follow up at higher resolution. So looking ahead in the further future, as I was already mentioning, there are plans for HRMOS or FLASH, which will be a resolution 60,000 multiplexing spectrograph with excellent blue capabilities. And I think for this type of science that I've been presenting, that will be exactly what this field needs. So that was the end of my presentation. Thank you very much for your attention, and I'm happy to take any questions.
Thank you a lot, Else. Thank you, really. It's a pity that we cannot clap for the in this virtual meeting. Very nice presentation. I see that there is a question by Rafael Rias. Rafael?
Yes.
Rafael. Sorry, not Rafael.
Can I ask?
Yes, please.
Sure, you're supposed to.
In one of your slides, you mentioned the carbon-enhanced metal poor stars. So do we always expect that these stars are one of the components of a binary system, or they can also exist as an isolated star?
Yes, thank you for asking that, because that is good to clarify. So as I said, for some of these stars, we think that is a product of a binary, where they transfer material, carbon-rich material from an AGB star to companion. But especially if we go to very low, which was what I was talking about there, what we see is that most of these stars, when we do radial velocity monitoring, for instance, that most of these stars are actually not in binaries. And so we think that this is genuinely a pattern that they receive from a previous generation. So for instance, from the first stars. And there's some theories that to why these first stars would produce more carbon or enrich their environment more in lighter elements. And it's not just carbon, it's also so for some of these stars there's a lot of abundance patterns there, and it seems to be that they're enriched in carbon but also in other light elements like nitrogen and oxygen and sodium, for instance. So they are related probably to these type of at some point I mentioned faint supernovae. So these are types of supernovae that we expect only to happen at the early universe, because these first stars are also a bit more compact. They might explode in a slightly different way, leaving exactly this kind of abundance. They are enhanced in light elements and a bit more depleted in heavier elements.
Thank you.
We have also a question by Lucas Bordone.
Yes, can you hear me?
Yes.
Yeah. Hi, Else. Thanks a lot. Very, very nice. And I'm not saying it because you're citing my paper. It's nothing to do with that. So I have a very quick comment. I absolutely agree with you that we should not lose resolution at this in the blue. I mean, the idea of removing basically the only instrument which is really efficient below 400 nanometers and goes past 40,000 resolution will create serious problem, in my opinion, in studying heavy elements in faint stars, because the regions are way too crowded. I think to do it properly around 20,000 resolution if the star is not very significantly metal poor. But I have a question. I find it very interesting what you said about having an alternate form to DDT and TO in a way, if I understand correctly, to follow up what comes out from instrument like for MOST, for instance. Can you expand a little bit on that? What would you have in mind in a way?
Yeah, so it's not a very formed idea. It's an idea brought up for discussion. So I was wondering if we should just focus the discussion on the instrumental capabilities, and I absolutely agree with your remark earlier that we need to keep a blue sensitivity. Yeah, so the idea is, I know there is the target of opportunity proposals. Are we ready to use that mode as often as we need to really do this kind of follow-up? Because I was thinking a bit about this whole process. I think this field will change quite a bit with the coming online of these multi-object spectrographs. And I think it's important for ESO as well, I think, to see how you can best benefit from this. And when you start to observe such high numbers of stars, you might want to think about a more automated way that you have some time reserved for interesting follow-up that will happen, that you know for sure that those opportunities will arise.
Thanks
I
a lot.
see that now there is also Vanessa and Amelia. Vanessa, please, both please try to keep in time, because otherwise we are going to be very late.
I think it's going to be very quick. It's to just highlight the fact that in the future of UVES, we should consider the fact that once Flames has been decommissioned, the fiber fed to UVES will go down presumably, and so this is a part of the interesting thoughts to be had about the future of UVES, I think.
Yes, absolutely. Thanks for highlighting that.
Amelia?
Yes, so a bit related to the operations of follow-up and things like that. I think we should look at what is being done in terms of brokers for alerts and things like that for the Vera Rubin telescope, right? There is a lot of work being done there on how to optimize follow-ups. And I think, well, I left Paranal quite some time ago, but the rapid response mode, I think, is a perfect tool for some sort of follow-up. I mean, there should be some compromise. But I think ESO has tools and the community has tools. That is a super good point that I think is a point for discussion, definitely.
Yeah, it doesn't need to be as rapid, right? And for this kind of rapid mode is of course envisioned for different types of targets. So it doesn't need to be that rapid, but you would like to observe perhaps before the star goes out of the sky again.
Yeah, for LSST, probably we will need rapid response also. So
for variable sources, yes, but I mean the things that I was talking about, less so.
Sorry, I don't want to, but I think it looks great for the discussion as a topic. If you don't mind, Else, thank you again.
Thank you.